Hi, I'm Mark Weitzman, and welcome back to Quantum Field Theory: A Student's Perspectives. Today we're going to do a deep dive on the Galilean covariance of the Schrodinger equation. Since we're going to do a lot in this course on Lorentz invariance and everything, it'd be nice to have an example where we use a group other than the Lorentz group, a transformation other than Lorentz transformations, and the Galilean transformation works well with the Schrodinger equation. It's not that often well known by students that the Schrodinger equation in fact is covariant under a Galilean transformation, but it's a very unusual transformation. In some ways, the Galilean group is more complicated than the Lorentz group. It seems like it's less symmetric, and as a Lie group, it has some differences. It has what's called a central charge, so the representations are a little bit different, and you can read about this in Chapter 2 of Weinberg's book or in Ballantyne's book on quantum mechanics and modern development. So let me start. Again, today we're going to do a deep dive. Galilean covariance or invariance. I don't want to get into the difference nowadays, but I spelled that wrong. Okay, so that's our topic today. And everything that I'm going to do here today is just an elaboration of what's done in section 4.3 of Ballantyne's book, Quantum Mechanics, A Modern Development. I highly recommend this book. It's one of my two favorite graduate level quantum mechanics book, along with the book by Steven Weinberg. They complement each other nicely too. Okay. It's also treated in other places, but it's also definitely treated as an exercise. It's treated as an exercise or a problem. In 8.04x, MIT's introductory QM course. So if you're taking that course, I would recommend adhering to the honor policy and not watching this video until you've gone through that exercise. But I think very few people here are taking a QFT course without having taken a QM course. Okay, so why are we interested in this? I said part of it was to show another example, but if we look at page 6 of Czerniecki's book, textbook, he says that for scalar fields, phi prime equal phi. Now, when I first read that, I was like skeptical of that, and I said, I don't think that's the case. And then I happened to come across the errata for the book, and the errata for the book says this is simply the simplest choice. Not the only choice. So today we're going to give an example where in fact this does not hold. What does hold is And what we usually want to hold is the absolute value of phi prime squared equals the absolute value of phi squared. Now, so let's first write down Galilean transformation, which is quite simple. X equal, and I'll define my symbols in a second. T equal T prime. And let's just ignore or carry along y and z. Let's say y equal y prime and z equals z prime. So a way to think about this transformation, again, imagine you have a coordinate system. Here's t, here's x, and then we have another system just moving along with a velocity v. Let's say we have a box and there's a particle in it or whatever. It's moving along with a velocity v, and it uses the coordinate system t prime and x prime. So these equations simply follow. If we want to know what x is, it's just x prime plus vt prime. This is going to be equal to vt, which is equal to vt prime. So under a Galilean transformation, this equation is the key difference. We have one universal time, but don't let that throw you. You still have to, when you're defining Jacobians and everything like that, you still have to treat the variables t and t prime as different, as I'll explain in a second. As a matter of fact, the first thing we want to do in when we have a transformation like this is let's compute the Jacobian. Oh, before I do that, what I want to show is we want to show that the probability density, in other words, if the particle's in a box, it's in a box. So we want to show that the integral of psi of x comma t, absolute value squared, dx is equal to the integral, the absolute value psi prime, x prime comma t prime, dx prime squared. In other words, we want the probabilities to be the same. Now, this is often not easy to do. We saw, for instance, in chapter 1 of Schrödinger's book, we saw that the actually, I'm not sure if this was covered. I think it was covered in chapter 1 of Schrödinger's book, but it's covered in every QFT book very early on. We saw that the Klein-Gordon equation which is relativist Lorentz covariant, does not have a positive definite conserved current. In other words, there's no probability density that we can use for the Klein-Gordon equation. It will turn out that the equation is still valid, and we can associate, instead of associating the current density with the probability, we can associate it with the charge density. The charge density can be either positive or negative depending on the charge, so that explains why we don't have positive definite. But, and this led, just a little bit of history here, this led to Dirac's attempts and his own equation. Because the Dirac equation is Lorentz covariant and also has a positive definite probability, conserved probability current. But it has its own problems, namely negative energies and four components and various other problems. So it ends up, as we've saw in our attempts at a relativistic quantum mechanics, it's just not going to work unless we go to fields. But getting back to our story here, for non-relativistic quantum mechanics, we will be able to have this relationship maintained, and that will be our goal. Now I just want to get back. Let me copy that Galilean transformation here. Well, I thought I figured this out, but I guess not. Let me try that again. All right, never mind. Okay, so I'll write it again. X prime equal x minus vt, t prime equal t. So let's just compute the Jacobian of the transformation, see if the measure changes. By our usual definition of Jacobian, it's the determinant of this expression. So I'm defining my sort of transformation as going from x comma t to x prime t prime. This is our Jacobian using the equations that we have. Partial of x, well, okay, I wrote it the opposite way, so I should invert, but if you invert these equations, you can see x equal, let's say, x is equal to x prime plus vt equals x prime plus vt prime, and t equals t prime. So the partial of x with respect to x prime is 1. The partial of x with respect to t prime is v. The partial of t with respect to x prime is 0 because t is t prime, doesn't depend on x prime. And so this equals 1. So our measure doesn't change, and that's why when I boosted this thing, I didn't say psi prime times the I didn't have a measure in here because the measure is going to be the same. Okay. Now, so what we want to achieve is a transformation. We want a transformation between psi of x comma t and psi prime of x prime t prime. So psi of x t is what we use in one reference frame, and this is what we use in the other reference frame. And I'm going to define it. I could define it in the inverse way also, but I'm just going to define it. Right now we don't know what the transformation is, except we do know one thing. We do know, well, we know this. In order to have this, because the measure is the same, the implication is that such that the absolute value of psi of xt squared equals the absolute value of psi prime, x prime, t prime squared. This is our condition. So the only way to satisfy this is there has to be a phase difference between psi and psi prime. So psi of x comma t, we can write it as e to the I, some function, some phase function of x prime, t prime will be completely general, times psi of x prime comma t prime. Our only condition is that f is real, because we want this to be a pure phase. Okay, and our Schrodinger equation is minus h bar squared over 2m, the second partial of psi with respect to x2, plus wx. I'm using the symbol w for the potential instead of v, because we're using v as velocity, so I'll just use w. And you know what? W is a function of x and t. Psi is a function of x and t. So this here is our Schrodinger equation. And what we want to do is we want to substitute psi in here and see if we get the Schrodinger equation in the prime system. So this is just a matter of this is sort of a matter of plugging and chugging and everything. From our I'm going to try this one more time. I guess I got to use the pen. Okay. Finally. Learn something new every day. Software is not my strong point nowadays. Okay, so we have partial derivatives with respect to x, and we have partial derivatives with respect to time, and we're just going to use the chain rule. So the partial with respect to x is equal to the partial with respect, I needed the other one, times the partial of x prime with respect to x. Let's see. This is where it can get confusing. Plus the partial with respect to t prime. Okay, I take the derivative with respect to, take the derivative of the function with respect to x prime, and then I take it with respect to t prime. Times the partial of t prime with respect to x. Okay, now this is equal to the partial with respect to x prime. I think I did this up here. Well, I did it in the thing there. Okay, so here I want, again, I really want x prime equal to x minus vt and t prime equal t. So this is the partial of x prime with respect to x is 1. The partial of t time with respect to x is 0. So we have this term here. And now I have the partial with respect to t is equal to the partial with respect to x prime times the partial of x prime with respect to t plus the partial with respect to t prime times the partial of t prime with respect to t. And this is equal to the partial with respect to x prime. The partial with respect to x prime with respect to t from this equation is minus v. So I'll put minus v. And now the partial of t prime with respect to t is 1. So this becomes partial with respect to t prime. Okay, so that's how we convert our derivatives. You might remember this one especially is just a co-moving derivative. Should be familiar from fluid mechanics if you studied that. Okay. Now, we have our Schrodinger equation over here, and we're going to just substitute in that. So, minus h bar squared over 2m, the second partial with respect to x prime squared. And now, our psi is e to the if psi prime. So I'm not always going to write the arguments here, but plus w times psi e to the if psi prime. Okay. Now this is equal to I h bar partial with respect to t of psi. So from this equation over here, it should be clear that this implies also that the second partial with respect to x is equal to the second partial with respect to x prime. That's why I just went right to this, because partial derivatives with respect to x don't change. It's only those with respect to t that change. So we have IH bar, the partial with respect to t of psi. We have the partial with respect to t is here. So I have IH bar the partial with respect to t prime. I'm just changing the order of this term. Minus v, the partial with respect to x prime, applied to e to the if psi prime. Okay, so that's our Schrodinger equation. And now the only thing we need to do is to just work these things out and go all the way through it. I'm actually going to, against maybe my better judgment, but I'm just going to go ahead and see if I can calculate on the fly and get it correctly. So let's just see how it works. So I have minus h bar squared over 2m. I'm working on the left-hand side now. And I'm going to take one derivative first, the partial with respect to x prime. Now the first term I have is, I'm going to apply it to here. So I'm going to have I, the partial of f with respect to x prime, e to the if psi prime. It's our first term. Plus e to the if, the partial of psi prime with respect to x prime. Okay, that's good. And then, I rewrote. Okay. So I'm rewriting my Schrodinger equation. Well, it's written correctly here. Over here, Okay. Okay. So now I have plus, and now I have to discuss something which I left out. Let me go back here. I am going to assume that w of x comma t is equal to w of x prime comma t prime. That is, we're going to assume that the potential doesn't change. I don't want to get into the complete justification for this. It can be justified. We could also simply work with free particles and get that, and then say adding a potential that's invariant will not change the invariance or covariance of the Schrodinger equation under a Galilean transformation. But for now, I'm just gonna. This is just an assumption, and it can be justified. Okay. So here I have plus w prime psi prime, which is just e to the I f psi. And now, so this is the left-hand side. This is equal to I h bar. And now I have, I'm going to apply the partial t prime first to the exponential term. It's going to be I partial of f with respect to t prime times e to the I f psi prime plus e to the I f, the partial of psi prime with respect to t prime. And now I'm going to apply this operator to these things. So I get minus IV, the partial of f with respect to x prime, e to the IF psi prime. And then I get minus V e to the IF partial of psi prime with respect to x prime. Okay. So now I have one more derivative to take, I guess. So let's do it again. Minus h bar squared over 2m. And now I have, so let's see how many terms we're going to get. I have 3 factors here, so I'm going to get 3 terms from that. And then I have 2 factors here, so I should get 5 terms altogether. Okay. Minus h bar squared over 2m. I, second partial of f with respect to x prime squared. Then I get minus, now I'm going to have an I coming down with an I. And it's going to hit that, so it's just a minus the partial of f with respect to x prime, but I already have a partial of f with respect to x prime, so this is going to be squared times e to the IF psi prime. And then finally I get plus I partial of f with respect to x prime, e to the IF partial of psi prime with respect to x prime. So that gives me the first 3 terms. And then I have plus, I'm going to get I partial of f with respect to x prime, e to the IF partial of psi prime with respect to x prime. And then we get the final term, plus e to the IF, the second partial of psi prime with respect to x prime. And then I have plus w prime e to the IF psi. And this whole thing is going to be equal to everything that's on the right-hand side here. Let's see if I can do this without messing up. didn't work. I gotta do it within 2 seconds or it fades away. Okay. Okay. So this is our big, seemingly very messy equation, but it's not really that messy. And I see I already made a mistake. I took the second derivative here, but I left out the e to the I f psi prime in the first term. So now let's every term has an e to the if here in it, so let's just cross them out. E to the if, e to the if, e to the if, e to the if. Excuse me. Okay, good. Now, let's rewrite it. Minus h bar squared over 2m I, second partial of f with respect to x prime squared, psi prime, minus the partial of f with respect to x prime squared, psi prime, plus, these two terms are the same, I partial f and psi prime, plus, so it's plus 2I, the partial of f with respect to x prime, the partial of psi with respect to x prime. And then I have okay, I have plus w prime psi prime. Should be a prime here. Everything should be primes here. And now this is equal to I want to take this term first, reasons I'll explain. This is equal to I h bar partial of psi prime with respect to t prime. Okay. And then here I have an I and an I, so that's a minus 1. So it says minus h bar, the partial of f with respect to t prime, psi prime. And now I have a minus I and an I, which gives me a plus 1. So I have plus h bar v, the partial of f with respect to x prime, psi prime, minus the last term, I h bar v, the partial of psi prime with respect to x prime. Okay, so this is our equation that we want to hold. And for some reason, I'm having trouble understanding why. I should be able to cancel the I want this term, this term, this term, this term. Okay, I have to look at this term, this term, this term. That's good. What I want is somehow I'm missing, there should be a term minus h bar squared over 2m second partial of psi prime with respect to x prime. Somehow I lost that term. It's over here. Okay, so this term, I'm writing it outside the bracket, minus h bar squared over 2m, the second partial of psi prime with respect to x prime, 2. Okay, so this belongs on this side of the equation. So now this plus this and this, these three terms are the transformed Schrodinger equation in the x prime t prime frame. So we can cancel these three terms here because this plus this equals that. So I can cancel that. And now I'm just going to bring everything here onto the other side of the equation. We get one big nice equation. Not too nice. Don't freak out. You might think we're getting nonlinear equations and everything, but everything will simplify. And the reason why everything will simplify is because there is a symmetry here. If we weren't working with the Schrodinger equation, if you were to do this with certain other kinds of differential equations, you find that they wouldn't be invariant under a Galilean transformation. So only certain special equations will be able to solve this huge equation here. So that's all that's left on the left, and now we're transferring these three terms to the right. So I have plus h bar partial of f with respect to t prime psi prime minus v h bar partial of f with respect to x prime psi prime. And I have plus I h bar v partial psi prime with respect to x prime. This equals 0. So this is our resulting equation. That we need to solve. And it looks like a mess, but as I said, it will turn out to be easier than we think. So now let's start looking at this equation a little bit more. We have to find an f so that this equation is always satisfied. Psi and psi prime are in a sense independent. One way to think about this is we have, at least for the spatial variables, we have a second order differential equation, the time independent Schrodinger equation, and to solve that we need to give a derivative of psi. Well, to solve it time-wise we need to just give the derivative of psi, but in a sense psi prime and the partial of psi with respect to x prime, this is hard to explain. They're not really independent, but if we can satisfy each of these coefficients separately, and we will be able to, then we'll be able to solve this differential equation. So for now, treat them as independent variables. And also, we have to find an f. Always. As we want an f, we want to solve this equation. We're going to choose an f so that this equation will always be solved, regardless of what psi is and regardless of what psi prime is. So that's our mission, and it looks tough, but we have to make use of the fact of f being real. So that will simplify things. So let's start by looking at the coefficient of the partial of psi prime with respect to x prime. Okay, this has a psi prime, this has a psi prime, this is psi prime with respect to x prime. So I get minus h bar squared over 2m 2i, the partial of f with respect to x prime. Okay, and then I have plus, this is the only other term which has a partial of psi prime with respect to x prime, plus I h v equals 0. So this equation, after you simplify it algebraically, we can cancel an h bar, and we get minus h bar over m, and we can cancel an I. And the 2 cancels as well. So I have minus h bar over m, the partial of f with respect to x prime, plus v equals 0. So that's one of our equations. This looks pretty easy to solve, actually, and it is. Now let's take the coefficient of psi. So here I have psi prime. Here I have minus I h bar squared over 2m, second partial of f with respect to x prime, plus minus sign, and minus sign is going to be a plus here, so I have plus h bar squared over 2m, the partial of f with respect to x prime squared. Okay, and now that's a derivative. I have plus h bar, the partial of f with respect to time, and I have minus v h bar, the partial of f with respect to x prime equals 0. So that's our second equation. I don't know why it does that. Confusing to me. Okay. But this equation is really 2 equations, because we can take the real part and the imaginary part. So the imaginary part is only one thing, is this part over here. So this implies that the second partial of f with respect to x prime is equal to 0. And then we can take the real part, the real part of all these, because f is real. That's here's where we're using the reality of f. So the other equation is h bar, I'm canceling on h bar here, h bar over 2m partial of f with respect to x prime squared plus the partial of f with respect to t prime minus v the partial of f with respect to x prime equals 0. Okay. So now we have, let's call this equation 1. Let's call this equation 2. And let's call this equation 3. These are the three equations we have to solve. Okay. Let's start with equation 1. That's pretty easy. So equation 1, we can rewrite that as the partial of f with respect to x prime is equal to mv over h bar. So this implies that f is equal to, this is just constants, it's equal to mv x prime over h bar plus some function of t prime. Okay, so that's good. And the real good thing about this is that this also satisfies equation 2. I doubt I spelled that right. Because if we take the second partial of this with respect to x prime, we're just going to get 0. So we have an f now. It satisfies equation 1 and equation 2. And we just have to go to equation 3. So let's plug it in. Let's plug in the f we have here into equation 3. So I have h bar, this is equation 3, h bar over 2m, the partial of f with respect to x prime, we already know that's mv over h bar squared, plus, now I have the partial of f with respect to t prime. This doesn't have a t prime. So that's just the derivative. I don't even have to write it as a partial derivative because g is only one variable, minus v, and the partial of f with respect to x time, again, we know is mv over h bar. So this is equivalent to the derivative of g with respect to t prime is equal to, this is a minus mv squared over h bar, and this is a plus mv squared over h bar over 2. So this over here ends up being minus 1/2 mv squared over h bar, and we put it on the other side, it becomes a plus. So this becomes mv squared over 2h bar. Sorry about that. So this has an easy solution. G of t prime is equal to mv squared over 2h bar times t prime plus some constant c. Now we're going to set c equal to 0 because we have f is it's just a phase factor, which you can cancel, just a constant phase factor, which is of no interest. So Finally, we have our solution for f. F is mvx prime over h bar plus mv squared over 2h bar t prime. And that's our solution. That shows that, in fact, we do have covariance of the Schrodinger equation. We can solve it. And I can also write this, if I substitute x prime, if I go back to the Galilean transformations and substitute what x prime is in terms of x and t prime in terms of x and t, we also get what it looks like, in those variables, which I'll need shortly, but you can verify this very easily. Very bad looking h bar. Okay, so we've accomplished our mission, and now I just want to go over what was considered a paradox. Some papers were published asserting a paradox, and the paradox went as follows. Look at free particles. Where W equal W prime equals 0. We know from the de Broglie, I keep on pronouncing that guy's name wrong, and I don't spell it right either. Anyway, we know from his work that P is equal to H over lambda, not H bar, H, because we're using lambda. You can also write it as 2 pi H bar over lambda. So, but we also know that a classical wave under a Galilean transformation doesn't change its wavelength. And you can see this, there's several ways to understand this. One way is, imagine you're in a plane flying over the ocean. Looking should be clear that the wavelength doesn't change. And basically the key thing is that T prime equals T. When we take a photograph, when we freeze everything at a given instant in time, both observers, they all observe the same instant of time. So it's not like we have a Lorentz contraction. So here at time t, I can look at a wave. We have like a wave moving along. There's the wavelength, let's say. Then here's another crest, another wavelength. Somebody moving along at velocity v, he might see them going that way, but he's not going to see any contraction of the wavelengths. So that's how a classical wave behaves. But we know that using this de Broglie relationship for particles, we know that P is equal to P prime, P is momentum, plus mv. How do we prove that? Well, I mean, we can just take the Galilean transformation. X is equal to x prime plus vt prime. So take a derivative. Remember, t is equal to t prime, so it doesn't really matter which one we use. dx dt is dx prime dt prime plus v. Now we multiply by m. So we end up getting that P is equal to P prime plus mv. So on the one hand, the paradox is that on a classical wave, the wavelength doesn't change, so the de Broglie wave momentum shouldn't change. But on the other hand, we also know just from ordinary transformations and mechanics that the momentum of a particle will change. It seems there's a contradiction between treating a system as both a wave and a particle. So there is a resolution to this, and the resolution is simply psi is not a classical wave. As a matter of fact, we saw that the amplitude changes. It has a phase factor and everything. So I want to show you right now how everything remains good. So let's take psi prime, x prime, comma t prime. We've already established that it's equal to e to the I. We calculate. Okay, let's take. Sorry about that. Thinking ahead. Let's take a free particle. So a free particle will have a form like this. E to the I, k prime, k is the wave number, k prime, x prime, minus omega prime, t prime. Now, if we have that kind of wave in the prime system, how does it look in the unprime system? Well, we just have to calculate. We already know that we've calculated that psi of x comma t is equal to e to the I f psi prime, x prime, comma t prime. Okay, so let me see if I can do my movement again. Okay, now this is equal to e to the I. Now I want to bring this down. Okay, so we calculated that earlier, or you calculated it. Psi prime, and now x prime is just x minus vt. We'll substitute in that, and t prime is t. Okay, So this is equal to e to the I mvx over h bar minus 1/2 mv squared t over h bar times e. Now we're using our definition here, times e to the I k prime times x prime, which is x minus vt, minus omega prime t, because t is equal to t prime. Okay. So now we just have to combine everything. It's equal to e. Gonna factor out I over h bar Okay, I over h bar. I'm going to get an h bar k prime times an x. So this should be, this is e to the I k prime x, e to the I k prime x. That's good. Then I have plus, I'll worry about that in a second, minus I over h bar. And I'm going to write this as h bar k prime plus mv squared over 2m times t. Now what I have to do is convince you that all of this is correct, and I need to fill in this term. So this is just an x term, which will come from here. So I need I mvx over h bar, so this becomes just mv. Okay, so we've established this, and we've established this. You know what? Let me do it another way. So this term, let's call this 1. Oops. 1 comes from 1 here. And this term comes from 2 here. Okay. Now, let's look at this term over here, number 3. When I square this, I get m squared v squared. I divided by 2m, so I get 1/2 mv squared times t times minus I over h bar. So the square of this right part here is exactly this, 3, which is good. Now let's square 4. When I square this one, I get h bar squared k prime squared divided by h bar. So I get h bar k prime squared minus I over 2m. Okay, so we get that because we make use, we make use of the relation h bar omega prime, which is the energy, E prime. And this is equal to p prime squared over 2m, which is equal to p prime is h bar k prime squared over 2m. So we get that omega prime is equal to h bar k prime squared over 2m. So I have, this ends up going to minus I omega prime, which is exactly what I want. Term 4, minus I omega prime t. The only thing left to check is that our cross terms are correct, because there's one last term here. So the cross term is minus I, the h bar is going to cancel that, k prime mv t over 2m. So the m's are going to cancel. And this is term 5, minus sign there, I k prime vt over 2. So this is checked. So this is 5, and this is equal to 5 on the cross term. So we've established now this expression here. And if you look at this expression, it simply says that psi of x comma t. Remember, we had a free particle plane wave with k prime and omega prime. So we have a free particle wave function. Let's call it k prime omega prime as the parameters. And now I get psi of x comma t is equal to e to the I. The h bar cancels out, so I have k plus mv over h bar k plus mv over h bar, and if we divide this by h bar, we also have that k is equal to k prime plus mv over h bar. So down here, this is a k prime. So this is really k prime plus mv over h bar. This is really k. And then I have minus I, and so I'm going to divide by the h bar again. So I have minus I over 2m k prime plus mv over h bar squared times t. Okay. And again, this is k. So this is equal to e to the I kx minus I. And again, we established that in the same way, this is equivalent. We could use the same formulas, and we get omega is equal to h bar k squared over 2m. So we have, I have, well, I think I lost my h bar somewhere. K prime plus, so I have minus I k squared t. Yeah, because that's a square, so I can't cancel that. So I need to go h bar. Okay, so the h bar is here. I have minus I h bar k squared t over 2m, which is equal to e to the I kx, and again, h bar k squared over 2m is omega, kx minus omega t. So everything works out exactly as it should. We've demonstrated it for a free particle at least, that there is no paradox in everything, that the way that momentum and wavelength and everything are defined for quantum waves ends up being different than for classical waves. The amplitude doesn't stay the same. It has a phase factor, and that results in everything being okay. So I know it seems like I did some hand waving here and everything like that, but I really didn't, and everything can be justified. But there were so many calculations, I had to pay more attention to the calculations. So thank you very much for watching this our first deep dive, and we'll have many more deep dives on more relevant things to quantum field theory. But it's good every now and then to dot all the I's and cross all the T's and make sure that everything seems to be kosher. I will see you. I've now completed week 0 to 2 on version 2, so I'll begin immediately working on scalar fields version 2, and we'll start with second quantization and discussing various things. Thank you very much.